All right. So welcome to the introduction to composite materials class that I will be teaching for these next few weeks. If I catch you on your phone, it's an automatic F. So try not to be on your phone. But throughout the presentation, if you have questions on terminology, I recommend. So all my slides after the title slide have a number with them. So I recommend writing down whatever terminology it is that you got stuck on and what slide number. So at the end of the presentation, we can go back to terminology. If you have questions other than terminology, then please interrupt me and ask. And at the end, I cover some of the terminology. And there's also a web page that is like an entire glossary of composite specific terms. But yeah, so let's get started. So composites, as the name implies, and some of you might have taken materials at this point, it's a combination of two or more materials. Usually the goal is to obtain the best properties of each of them. In the case of fiber reinforced polymers, which is what our the composites that we usually deal with are, and the most common ones. What you're trying to get is the strength from the fiber, which is usually carbon fiber, aramid, glass, boron, and you're trying to get the flexibility of the plastic or the polymer. I didn't cover it for this lecture, or won't cover it for this lecture, but there's a rule of mixture between the two where you can obtain mechanical properties based on each of them. So we try to maximize the mechanical properties of the polymer that we're using. Usually for us, it's an epoxy resin because it's the strongest of the resins. Because the rule of mixture, if we use something that's too weak, our overall composite will be much weaker. So yeah, in our case, the goal is the lightest, strongest part. So the strength to weight ratio for us is what really matters. And actually that picture on the right is BMW i3 chassis. It is made out of carbon fiber, reinforced polymer. And it's pretty darn cool. All right. So composites in general are made of matrix and reinforcement. Or the reinforcement is also called a dispersed phase. So in our case, the matrix, like I mentioned, is a polymer, and it's usually a type of resin. So epoxy, vinyl ester, polyester resins are the ones that we usually use with our composites. And the fiber is carbon fiber, glass fiber, aramid fiber. Aramid is usually known as Kevlar by its kind of its trade name, I suppose. So the purpose of these two in a composite is that the matrix, or the polymer, the plastic, transfer the stresses onto the fibers in case of the fibers from the environment. It also doesn't allow the fibers to move in space. So all of you have taken statics, or, well, I guess Michael hasn't because he can't be, but he has a rough understanding of stress, I would assume, by this point. So if you think about this, you know, like if I'm applying, so if I'm applying a tensile force in this direction, then it becomes pretty clear that the fibers would be the ones stretching. So that direction I would have really high strength. And in this direction, the fibers actually are trying to separate from each other. So this distance is trying to increase. And in that case, the polymer, the matrix, is the one that's going to determine the strength the most. So that's also why it's important for us to pick a matrix that is still not very weak, but just weak enough for us. So yeah, and the fiber increases the mechanical properties of the overall composites the overall composite usually. Right, so short intro to materials. So materials obviously have properties associated with them. Usually we call them mechanical properties in this case. The resin and the fiber both have their own mechanical properties. And usually how we obtain those mechanical properties are through various sources of testing, and you can see kind of these. Tension, shearing, torsion are probably, and bending are the ones that we use in composites. Compression is a bit weird because it gets close to buckling when it comes to composites. The two are very similar, but in any case, I would give a brief introduction to Hooke's law. I think most have covered it. I don't know if Michael has any classes that covered Hooke's law. Probably not. In any case, this is recorded, so it's also for people that did not come. So, brief introduction to Hooke's law. Usually in mechanical systems, and in the case of materials testing, yeah, you took mechanics. Okay, cool. But in any case, we have, let's say we have a force that's being applied across this element for the sake of just simple, to keep it simple, we're going to call this to be a metal. So let's say this is steel. And this is actually analogous to a spring. So it's pretty much the same as me applying a force across a spring. So Hooke's law, usually in high school, is represented by the force across the spring. So that's usually the statement that is used in high school to represent Hooke's law. However, in materials, similarly to this K constant, you have a constant on this side that is also related to a force and to a sort of displacement. Except in materials, when you're actually applying this force, on a spring it doesn't matter, but on a material you have a certain cross section associated with it. So let's say this has an area A. So if I'm applying a constant force and I increase this area A, there's more material for me to distribute that load around, which means the overall stress is lower. So the statement for Hooke's law in this case actually has to take into account the area. So what we end up doing is that we divide essentially both sides by this area, and this K constant now. Sorry, that's a bad way of explaining. I'm just gonna make them analogous. I'm not gonna divide the right equation. Bad, Thiago. Right, so there's an area associated with it. So usually we're concerned about the stress that's being applied on this, and it's usually represented by a sigma. So sigma is in units of PA, or any multiplication from this, or pound per inch squared PSI, yes. Or commonly K is high because these values tend to go pretty high. But in any case, the statement for material of Hooke's law is that the stress on it is equal to this constant E, which is usually known as Young's modulus or the elastic modulus, times the strain. This is a lowercase sigma. And this strain, so if I have this length and I pulled it with a certain force, I deformed it by a certain amount. So I have delta X plus L. Let's say that this is delta X while I'm applying a force to it. So based on Hooke's law, that strain actually ends up being just the delta x, but really it becomes the new length, which is so it ends up just being delta x over L, and this is unitless. Any questions at this point? I think y'all probably covered in physics something like this. I don't know. I know for mechanical engineering we covered in statics, solids, materials. So yeah. But in any case, the strain is unitless. It's just taking into account how much I deformed based on a certain force. So with this statement now, we can tell that this is linear. So if I were to plot this, this is sigma. It would look something like this. What would the slope be?
E.
Yeah, it would just be E. So if you were to plot the same for a spring, exact same thing, except now, you know, we don't have a length here, but rather we have a unitless form of measuring a deflection. Now, if I were to, you know, apply a certain stress that gets up to this point right here, and then I release the force, what will happen to my material? So it's still acting like a spring, right? So what will end up happening is that this material will actually be able to move back and forth along this line and return to its original length. So that's a pretty big property of materials, and this is called, for that reason, the elastic region. So this elastic region. However, for materials, there becomes a point that I end up applying too much load onto it, and at that point, it actually starts deforming, and it's no longer linear. So Hooke's law only applies from here to here. So once we get to this point, there's no more empirical formula. So there's no more Hooke's law for us. And then, you know, I'll keep applying a stress, and what this graph is telling me is that I'm not applying that much more stress, but my part is deforming significantly. And I have a video later on that will show this. And it will come to a point where simply it will break. And then this will, I mean, in testing, will just come back down to zero, because now the part can't resist anything anymore. This is the case for steel. So what these 2 points mean, they're actually called strength of the material. So the elastic modulus usually represents that spring constant of the material. Once we go past that point and we enter, so we go from elastic and we enter the plastic region, and Hooke's law doesn't apply anymore. What this implies is that from this point on, our material cannot go back to its undeformed length. So we pass this point, the material is kind of gone. And this is very observable in metals. If you start stretching steel like significantly, it becomes a point where if you let go, it won't come back. And it's steel and metals, it's pretty cool to see. So this would be what the stress strain curve would look like for a metal. This is what it would look like for a composite. So much like a metal, we're going to have a linear section to it, and then suddenly our composite's going to fail. There's basically no plastic region for a composite. Once it starts creating these things called voids inside the material, so once it starts actually separating the physical like atom connections, Once it starts actually separating that chemically, in a composite, it will fail. In a metal, it's still able to take some more load. It won't come back to what it was before, but it can still keep going. It can still exist, and we can actually visually see it happening. In a composite, it will simply break out of nowhere. Pretty much no like notice of it happening. So it's pretty scary. But yeah. Any questions on Hooke's law, stress strain at this point? This is kind of a brief overview. So usually there's 2 points that we call here. So the point at which it fails and the point at which it goes from elastic to plastic. So the point at which it fails is usually called the ultimate strength. So like the name implies, the last pressure that you can apply to a material. Whereas the blue, or the first one, is called the yield. So in a composite, yield and ultimate usually don't exist because it simply breaks. But for a metal, it's pretty important for us to have that discerning. So like a good example is the frame. It so happens that, you know, if you go onto this plastic region, what's happening is that since the energy is no longer considered a spring, so it's not just storing energy and releasing it back, it's actually dissipating energy. So if you think about it in a car crash, your car will deform significantly. So it's going to enter the plastic region. The reason it does that is because it's dissipating all of that impact energy by destroying itself instead of the energy going onto you. So in composites, we absolutely do not have that. So it's poo-poo for that. So the yield to ultimate, so this difference here is pretty important to know for a metal. It helps with design quite significantly. But that's pretty much all I wanted to cover on Hooke's law. So let's go back to the PowerPoint.
Oh, I have a question.
Go ahead.
Is the ultimate tensile strength like different from the ultimate strength then?
I'm sorry, could you repeat that?
Is the ultimate tensile strength different from the ultimate strength?
Tensile just means we're doing it in the tensile direction. For metals, they end up all being the same. Because what happens with metals is that they have the same properties in all directions. The compressive strength of a metal ends up being, okay, sounds good. The compressive strength ends up being the same for a metal. It's very different in the case of composites. Because composites, as I will probably cover later on, they don't have the same properties in basically any of the directions. You can estimate it to have 3 directions that have the same properties. But even then, that's an approximation. It's not true. But in order for us to be able to compute anything, we have to make some assumptions. But yeah, so this is kind of that stress strain curve that I was talking about for a metal. So it starts elongating, and then, you know, after that part, that's yield, and then it still has some before it gets to the ultimate, which is right around there, and then it just breaks. For composites, it does not do that. The resin kind of does that. The resin gets to a point, so it's a plastic. Actually, if you have taken materials lab, or if you will take materials lab, when you get to test high density polyethylene, something like that. Basically a cutter board, like cutting board material. You actually put it on the tensile test and you start stretching it. If you stretch it really fast, it breaks really easily. But if you do it slowly, it just, like, I think our sample started at like 50 millimeters and ended with like 500 millimeters. It just keeps like stretching out and doesn't break. So the resin does something similar to that. The fiber pretty much only Hooke's law. And since the fiber dominates the tensile direction, it ends that the actual composite also basically only does Hooke's law and then breaks. So we covered those two. So material strength, Young's modulus. Young's modulus just basically represents that slope on the stress strain curve. So why do we choose composites? So I mentioned in the first slides that we usually want something that's light and strong. So if you were to plot, so these are kind of in a log scale, but basically composites in terms of density are only, the only lighter materials are wood. And then you go into concretes. Concrete is technically still a composite, if I remember correctly, which is a weird thing. And then you have the metals. So the metals obviously very, very heavy compared to a composite. But then if you go into the tensile strength and the tensile modulus, composites actually directly compete with steel and aluminum pretty closely. Even if you get to boron composites, they actually go even stronger than steel. But they cost a fortune and aren't really produced anymore. So why use them? Why bother? Whereas carbon is way more commonly available and still matches steel pretty closely at much lower weights. Similarly for the tensile modulus, so for that E value, it's right up there with the other ones, with metals. So in terms of within the composites themselves, the three ones that we tend to focus the most are E-glass and S-glass, which are two different types of fiberglass. Then you have aramid, which is Kevlar, or Twaron, which is another brand. And then you have carbon fiber. So these three are usually the ones that we end up using and most of the industry uses as well. In general, carbon is the go-to for pretty much everybody. It's the one that's growing the fastest out of all of them, which means it's also more readily available, which means we got it for free. Thank you, Michael. Very nice. And actually, these names are just commercial names to them. The one we actually got is the T300, which is a common modulus carbon fiber from Terray. AS4 is one from Hexcel, which is a different company. But they're pretty much all like standard. Actually, ANSYS has built into their library something that is close to both of these. So it's very easy to actually run simulations with them. And in terms of, so this is just a chart comparison. Carbon fiber, the only thing that's really considered poor is the price, which again, free for us. Everything else is excellent to good. Abrasion resistance, fair in terms of it's easy to cut through with it with abrasives, which for us is actually pretty good because then we can cut the carbon fiber to shapes that we want. The excellent aramid ends up hurting us because if we try to cut it, it becomes harder for us to cut, but it's very good against something that's rubbing on it constantly from actually breaking the composite. But, and then, you know, conductivity, it's great for conducting electricity, hence why we do not use it in array or battery box. So this is a structure with efficiency. The base level was static aluminum, and you can tell that carbon compared to aluminum and even titanium is way more efficient in terms of, I think the metric that was used for this was the strength to weight ratio of them. So titanium ends up being a little bit heavier than aluminum, but it's way stronger, whilst carbon and epoxy end up being much stronger than aluminum and much lighter than aluminum. So it's a double win on that front. Fatigue life is usually really bad for metals, especially aluminum. Steel is still pretty good, while carbon and carbon fiber, fiberglass, composites in general, usually fatigue life is one of the best properties. Another reason why they're very widely used in the aerospace industry. So why not composites? Some of the downsides, usually really high costs. If we were buying this, it would be a large chunk of our budget. It was a large chunk of our budget before we got the donation. So it's usually prohibitive if you don't have funds or if you can't get it for free. And funnily enough, if we were to try to get similar amounts of metal free, we probably will not be able to. Nobody wants to donate metal, as it turns out. Another thing, like I drew when we were covering Hooke's law, is that it does not yield. It simply goes from linear to complete fracture, complete failure. The properties are not the same in every direction. And there's these two terms, orthotropic and anisotropic. They describe properties of materials. In short, orthotropic means it's got three directions of material properties, so an X, Y, Z. Anisotropic basically means that every direction is different. So composites, in reality, are anisotropic. We can approximate orthotropics if we're using unidirectional fibers, which we are not. Those are really difficult to obtain. So there's a somewhere in the middle of those is where we actually analyze the composites that we use. Another thing, they're really difficult to work with. They're hazardous to human health. Breathing in carbon fiber, fiberglass, Kevlar dust is horrible. It will fuck up your lungs. I've breathed a lot of it in already. I've learned my lesson. I actually already developed an allergy to epoxy from using it too much. Not like bad allergy, but it's not great to have it, you know. So PPE is like super important. Like when you're doing metal work, if you've gone to the machine shop, pretty much the only thing you need is, you know, covering for your eyes and something to cover your legs to make sure you don't get hot chips on you. When you're working with composites, it can range anywhere from respirators and just goggles to full-on bunny suits because of how bad they are for your health. It's also really difficult, non-automated manufacturing. Tiny mistakes will compound to an absolute horrible part. My dog is crying a lot. Anyways, whereas in metals, you know, we have CNCs nowadays that can do a lot of work if you program them right. There's no such thing as a CNC. There's automated fiber placement in composites, but even then, it doesn't apply for really complicated geometry, such as a car. For airplanes, pretty easy to do it. But yeah, and it is harder analysis than metals for proving that they're safe, mainly because of the properties not being the same in every direction, and any tiny mistake in manufacturing will render your composite from really strong to about as weak as a plastic. And I actually wanted to show, so on the left, it's actually a metal in a tensile test, and you can kind of see that necking happening. So the necking is the process in which the metal is, you can see the area slowly becoming smaller at the center. So if I were to crash a car and I go in and inspect the frame afterwards and I look at it and it's deformed, I know it's gone past its yield strength. I know now that I should replace it. If it hasn't, I can, you know, visually inspect it and see, oh, none of these yielded, I'm probably good. Whereas in a composite, this is what happens at break. So if our car crashes and we create tiny fractures, so right around before it breaks, what's actually happening is that in between the fiber matrix, you're creating voids where you essentially create a tiny crack in there. And let's say that I stop loading at this instant, it won't return, like that void has already started creating. I have no way of inspecting it. I have no way of making sure it's safe. So in the case of a crash, if the composite doesn't fully break, you still kind of have to trash it. Obviously, in the case of body panel or body work, not a huge deal. In the case of a monocoque, it is a huge deal because that is the structure of the car. So yeah, it's pretty. I don't know if y'all can actually hear the thing happening or not. I don't know if I shared. No, sad. It's fine. It actually makes a pretty cool noise. Let's see if I can share. Yeah. All right. Y'all ready? This is probably going to be really loud on y'all's end. That's what it sounds like. It's just like somebody shot a gun, and that was the composite breaking. Yeah. So, last thing I wanted to cover for this lesson was some common terminology in composites and composites manufacturing in general. First one is fiber cloth. So usually that's what we acquire. That's what actually are the carbon fibers, the fiberglass and whatnot. It usually is referring to dry fibers for the most part. That means that no matrix has been added to it. And usually it also comes woven. So the type, so woven fibers are essentially similar to like a woven basket. It's pretty much just fibers interlaced. They're oriented in certain angles. 0-90 is the most common, and I think it's pretty much the only one we'll find available. So basically, you know, I have a strand of fibers that's going in this direction, and I have another strand that's going in this direction, and I'm just interlaced like up and down. For plane weave, you can actually see that right here. Basically, this is fiber going across, and the small circles are the fibers coming in the direction that we're looking at. So this is what's called plane weave. The twill weave is a little bit different. It basically does 2x2 or 3x3 or 4x4, where it's just doing them like it's minimizing how much curvature the fiber that's in the middle will take, which is good for parts, and it is a little bit better for curved parts, especially. Right, and then laminates are stacked among fiber reinforced sheets. So a single ply would be one of these weaves that I put matrix onto it. And then if I stack that on top of another ply or another lamina, it becomes a laminate. So the laminate is actually the stacked sheet. So whenever we're doing a manufacturing, we can't just go with a single sheet because it likely won't be strong. And as we'll see later, it will only cover two directions, so 0-90. So usually we're stacking them in a way to try to achieve a metal, to try to achieve having the same properties in all directions. Go ahead, Michael.
So do you know if, just trying to relate it back to real life, if somebody says that like a floor is like laminate or laminate paneling, is this the same context?
Somebody says a floor is laminate?
Yeah, like not hardwood, but it's laminate. Is it actually stacked fiber reinforced sheets?
I'm not sure. Part of what it's called laminate is that it started as flat plates, but I'm not sure on that. Yeah. So it's actually a nice video of us putting bevel into an autoclave where it still sits today. Look, it's Matthew and Michael right there. Right, so layup is the manufacturing process that usually involves dry fiber and a resin. In this case, it would be called a wet layup, where essentially the concept is we're going to place the woven cloth, so the woven fibers onto a part, onto a mold, and then we're going to put resin on that. And then we're going to keep doing that with all the plies that we have until we form that laminate. Funnily enough, a dry layup is when we actually use pre-impregnated fibers. And pre-impregnated fibers are basically fibers that have resin already chemically infused in them. So it's a great way of controlling how much resin you're putting per fiber, because that will affect your mechanical properties. And the resin is dormant while it's stored at low temperatures. And when I say low temperatures, I mean like 0 Fahrenheit. So in the negative Celsius is the ideal storing temperature. And even then, they expire after production within 2 to 3 years. It's very easy for us to get that, because it expires by aerospace standards. And aerospace standards are really high. Our standards are hella low. We're not flying. We're not carrying passengers. We don't have an overseeing body that regulates every single thing we do. So in order for us to pass with a part that has pre-preg, our standards are much lower. So anytime they expire, usually aerospace companies, instead of just throwing them away, donate them to us at the regular value that they purchased them from, and get a huge tax cut for themselves. And we get a lot of pre-impregnated carbon fiber. The catch with pre-impregnated carbon fiber is that it requires heat and pressure to cure. So for a dry or for a wet layup, where I'm splitting fiber sheets and just putting epoxy on them, I can do that at room temperature, leave it to cure for a week at room temperature, come back, and I have a good composite. In the case of pre-preg, I can leave it out for months. I can leave it out for years. If I don't add temperature and pressure to it, it will not cure. Or at least it will not cure properly. It will expire and it won't be strong. So it requires an autoclave usually, and that's actually when you see the bottom where we were loading V-volt onto. It's, in short, a huge pressure cooker. That's all it really is. But yeah. The other thing is the stacking sequence. So it's a way of representing the orientation of the fibers. So like I said, we usually want to stack them in certain angles. So you can see here basically 0, 45, minus 45, and this is for unidirectional. In the case of woven fibers, we have already 0, 90, and then we go 45, minus 45, 0, 90, and we keep doing that. So we basically have 2 plies in one, but they're not as good as unidirectional. And the last thing were sandwich panels. So I kind of mentioned this early on in the design process that we have to add that foam core in between. So what that actually does is that composites, as it turns out, by themselves are really bad in bending because their moment of inertia, since we're creating such a thin part because we're saving weight, their moment of inertia is really low, which means bending them is very easy. And they, on top of that, they don't have good flexural rigidity. So the bending test, if we were to do a composite, the actual modulus for bending is really bad in a composite. Now we can't really change that. So what we do is we increase the moment of inertia by adding that foam core, or a core in general. Honeycomb is another common used one. Essentially, we're not really adding to the property. We're just, or I mean, we are adding to the property, but we're not changing the chemistry of the composite. We are simply making it thicker so that it's harder to bend. It's like the dumbest thing, but it works so well. So we keep doing it. I don't remember if I have anything else other than that, because yeah, I was preparing this for a bunch of freshmen. So I am sorry, we go through it real quick. Let me stop.